More than 13 billion light years from Earth, in a patch of sky astronomers had photographed 100 times before without noticing anything unusual, the James Webb Space Telescope found a galaxy that, according to the standard timeline of how the universe is supposed to work, shouldn't exist yet. Not shouldn't exist in some vague, speculative sense. Shouldn't exist according to decades of carefully tested physics, describing how long it takes gas to collapse into stars, how long it takes stars to form galaxies, and how long it takes galaxies to grow bright and chemically complex enough to look the way this one does. And yet there it was, its light finally reaching Webb's mirror after traveling for more than 13 billion years, showing scientists a galaxy that one of the astronomers who confirmed it described in the title of the actual scientific paper as a cosmic miracle. This is the story of MOEM Z14, currently the most distant galaxy ever confirmed, and the broader ongoing puzzle it represents, one that a growing number of astronomers now openly describe as a genuine unresolved tension between what Webb keeps finding in the deep universe and what established models of galaxy formation say should be there. To understand why a single distant galaxy can generate this much genuine scientific debate, you first need to understand exactly what astronomers mean when they say something is 13 billion light years away, and why that distance is really a statement about time, not just space. Light travels at a fixed, finite speed, and space itself has been continuously expanding since the universe began, roughly 8 billion years ago, in the event cosmologists call the Big Bang. Because light takes time to travel, looking at a very distant object means looking at light that left that object a very long time ago, sometimes billions of years in the past. A galaxy 13 billion light years away isn't just far away in space. It's a snapshot of what the patch of the universe looked like when the universe itself was only a few 100 million years old, a direct physical window into the deep past, rather than a picture of that galaxy as it exists today. Astronomers measure this kind of extreme distance using a value called redshift, denoted with the letter Z. As light travels through continuously expanding space, its wavelength gets stretched, shifted toward the red end of the spectrum, and the more that light has been stretched, the further it's traveled and the further back in time it originated. A redshift of 0 represents the present day. Higher redshift numbers represent progressively earlier points in cosmic history. Objects with a redshift above about 10 are generally understood to represent light from within the first 500 million years or so after the Big Bang, an era astronomers often call the epoch of Ryanization, when the very first stars and galaxies were forming and beginning to light up an otherwise dark, gas-filled early universe. This is exactly the era the James Webb Space Telescope was specifically designed to study. Launched on Christmas Day 2021, Webb was built with a primary mirror over 21 feet across and instruments tuned specifically to detect the extraordinarily faint, heavily redshifted infrared light, coming from precisely this earliest chapter of cosmic history, light so stretched and so faint by the time it reaches us that no previous telescope, including Hubble, had the sensitivity to reliably detect and confirm it. Since becoming fully operational in 2022, Webb has repeatedly pushed back the record for the most distant confirmed galaxy ever observed, and each new record has tended to bring with it the same underlying complication. These extremely distant, extremely early galaxies keep looking considerably more developed, more massive, and more chemically complex than existing models predict they should be, given how little time had actually passed since the Big Bang by the point their light was emitted. In May of 2024, a research team working as part of the JWST Advanced Deep Extragalactic Survey, known as JADES, confirmed a galaxy called JADES GS Z14-0 at a redshift of 14, 32, corresponding to a time roughly 290 million years after the Big Bang, making it, at the time, the most distant galaxy ever spectroscopically confirmed. That discovery alone was remarkable simply for pushing the observable boundary of the universe back even further than before. But a follow-up study, published in the journal Nature Astronomy in March of 2025, and building directly on that original 2024 discovery, revealed something considerably more surprising than the galaxy's distance alone. According to that newer analysis, JADES GS Z14-0 turned out to be, in the researchers' own words, unexpectedly bright and chemically complex, containing a significant amount of oxygen, a heavier element that generally requires multiple generations of stars living and dying to produce in any meaningful quantity. Based on that oxygen content, the research team concluded the galaxy had likely already been actively forming stars for roughly 100 million years by the time its observed light was emitted, meaning star formation within this particular galaxy must have begun, even earlier than the already extraordinarily early snapshot Webb had captured, pushing the true beginning of significant star formation in this galaxy back closer to, or even before, the 200 million year mark following the Big Bang. As the researchers themselves put it directly, this finding implies that star formation began earlier than previously thought, directly challenging existing models of how quickly galaxies are supposed to assemble and mature in the earliest chapters of the universe's history. Then, in early 2026, an even more distant and in some ways even more puzzling galaxy was confirmed, one that has since become the current record holder and the center of the specific mystery this story is really about. Designated MOM 614, this galaxy was originally identified using Webb's near-infrared camera and subsequently confirmed spectroscopically using its near-infrared spectrograph. The same two-step process, initial detection followed by rigorous spectroscopic confirmation, that astronomers use to verify these kinds of extreme distance claims with genuine scientific confidence, rather than relying on a single, less certain measurement alone. The confirmed spectroscopic redshift came out to 1444, corresponding to a time roughly 280 million years after the Big Bang, edging out JWST Z14 as the most distant confirmed galaxy currently known, according to the research team's published findings, posted to the Open Journal of Astrophysics in January of 2026, under the direct, almost startlingly candid title, A Cosmic Miracle, a remarkably luminous galaxy at Z-spec equals 44, confirmed with JWST. That title alone tells you something important about how seriously the researchers themselves take the tension this discovery represents. According to NASA's own description of the galaxy, MOAM 14 is brighter, more compact, and more chemically enriched than astronomers had anticipated for an era this early in cosmic history. Among its most surprising specific features, researchers detected elevated levels of nitrogen within the galaxy's spectrum, a finding that suggests, according to the study, that massive stars may have formed and evolved considerably more rapidly in the dense early universe than current theoretical models actually predict is possible. The galaxy also appeared to have already cleared away the primordial neutral hydrogen gas immediately surrounding it, an unexpected finding in its own right, given that the broader early universe, at this particular point in cosmic history, was still generally thought to be filled with exactly this kind of neutral hydrogen gas, not yet fully cleared away by the ionizing radiation pouring out from the first generations of stars and galaxies. Put plainly, MOAM Z14 appears to be a galaxy that had already assembled, ignited, chemically enriched itself through multiple rounds of star formation, and begun clearing out its own surrounding gas, all within roughly the first 280 million years of the universe's entire 8 billion year existence, a length of time that, according to the standard, well-tested models astronomers have relied on for decades, simply shouldn't have been enough for a galaxy to reach this specific level of maturity, brightness, and chemical complexity. It's genuinely important to be precise here about exactly what's being challenged, because that precision is really the difference between an honest account of this discovery and an exaggerated one. As one recent overview of Webb's 2026 findings put it directly, addressing this exact question head-on, no, discoveries like this do not challenge the Big Bang itself, the well-established framework describing the universe's overall origin and expansion, a framework supported by an enormous, independent body of evidence, completely separate from any single galaxy's brightness. What these discoveries genuinely challenge is a considerably narrower, though still significant, piece of cosmological science. The specific models describing exactly how quickly gas collapses into stars, how efficiently those stars form within newly assembling galaxies, and how quickly those early galaxies are able to grow massive and chemically complex during the universe's first few hundred million years. That's a real meaningful scientific tension, one astronomers are actively working to resolve, but it's a considerably more modest, more precisely defined problem than the sweeping, all-encompassing framing that headlines built for maximum attention sometimes suggest. This isn't a problem confined to just one or two individual, unusually striking galaxies either, and that broader pattern is arguably the more scientifically significant part of this entire story. According to a detailed 2026 survey of Webb's cumulative findings, one of the clearest, most consistently reported results across several years of observation involves what astronomers call the galaxy luminosity function at high redshift, essentially a statistical measurement of exactly how many bright, massive galaxies exist at these extremely early points in cosmic history, compared against how many pre-Webb theoretical models predicted should exist. According to that survey, the bright end of that luminosity function at redshifts above 10 is measurably, significantly higher than pre-Webb models predicted, meaning there are considerably more very bright, very massive early galaxies scattered across the deep universe than existing theory allows for, given how little time had actually passed since the Big Bang by that point. Some assessments of this broader pattern have described the discrepancy as being roughly 100 times greater than what earlier theoretical models had predicted. A genuinely substantial gap between observation and expectation, one that can't easily be dismissed as a single unusual outlier or a statistical fluke involving just one or two remarkable galaxies. There's additional independent evidence reinforcing the same broader tension, coming from an entirely different kind of observation altogether. In June of 2026, 3 separate peer-reviewed studies published in the Astrophysical Journal Letters and presented at the 248th meeting of the American Astronomical Society confirmed that a galaxy cluster called XLSSC 122, located roughly 4 billion light-years away, represents the most distant strong gravitational lens ever directly observed, a specific type of astronomical phenomenon where a massive foreground object's gravity is strong enough to visibly bend and magnify the light from more distant background objects behind it. According to that research, the dark matter core at the center of this particular galaxy cluster is measurably denser than any standard cosmological simulation predicts it should be at this stage of the universe's development, with a discrepancy described as statistically significant at a level of 3. 2 standard deviations, a genuinely meaningful gap in the kind of careful quantitative language cosmologists use specifically to avoid overstating a result. Just as with the individual distant galaxies described earlier, this finding represents evidence of large cosmic structures assembling, organizing, and reaching a state of maturity considerably faster than the standard cosmological model, generally referred to by researchers as lambda CDM, currently predicts should be possible. Separately, in ongoing research described in Space, Comm's coverage of Webb's 2026 findings, astronomers identified a system of at least 6 separate galaxies actively merging together roughly 12 billion years ago, corresponding to a time only about 8 billion years after the Big Bang, a system designated TGSSJ 1153049. According to that reporting, this merging system may eventually grow into one of the largest galaxies currently known anywhere in the observable universe, and its formation appears directly connected to the growth of a young, actively developing supermassive black hole at its center, adding yet another layer of complexity to the broader picture of just how quickly massive cosmic structures, whether individual galaxies, galaxy clusters, or supermassive black holes, seem to have assembled during the universe's earliest chapters. Taken together, these findings, JD's GS Z14 Orio's unexpected chemical maturity, MOEM Z14's surprising brightness and nitrogen content, the broader statistical excess of bright early galaxies across the wider luminosity function, the too dense dark matter core within XLSSC 122, and the rapid complex merger already underway within TGSSJ 151 all point in a broadly consistent direction. As one recent overview of the field described it directly, there is a growing chasm between theory and observation related to the early universe, one presenting compelling, genuinely open questions that astronomers are actively working to explore going forward, rather than a settled, comfortable picture that Webb has simply confirmed and closed the book on. It's worth walking through, honestly and without exaggeration, what the leading proposed explanations for this tension actually look like, since astronomers studying this problem aren't simply throwing up their hands and declaring existing cosmology broken. Several genuinely serious, actively researched possibilities have been proposed. One leading idea involves the possibility that star formation in these earliest galaxies may simply have been considerably more efficient than current models assume, meaning a larger fraction of available gas gets converted into stars, does so more quickly than the standard star formation efficiency assumptions built into most existing theoretical models currently allow for. A related possibility involves what astronomers call the initial mass function, essentially the statistical distribution of how many small, medium, and large stars tend to form together within any given burst of star formation. Some researchers have proposed that conditions in the extremely early universe may have favored the formation of unusually large numbers of massive, extremely luminous stars specifically, which would help explain why these early galaxies appear so much brighter than expected without necessarily requiring an implausibly large total amount of stellar mass to have formed. Other researchers have explored whether rapid, efficient growth of supermassive black holes within these earliest galaxies might be contributing extra brightness to Webb's observations, effectively mixing genuine starlight together with additional light, generated by actively feeding black holes, a combination that could make a given galaxy appear more luminous and by extension more massive and mature than its actual stellar population alone would suggest. None of these proposed explanations represents an abandonment of the broader, well-established framework of Big Bang cosmology itself. Each one represents scientists doing exactly what good science is supposed to do when observations don't match predictions, refining and adjusting the more detailed, more specific models describing star formation efficiency, stellar populations, and early black hole growth, rather than discarding the overwhelming, independently verified body of evidence supporting the universe's overall age, origin, and expansion history. The distinction matters enormously, and it's worth being direct about it precisely because some corners of the internet have tried to frame Webb's early galaxy discoveries as somehow undermining the Big Bang model entirely. A framing that isn't supported by the actual scientists conducting this research, and one that conflates a genuine, interesting, actively studied tension in the specific details of early galaxy formation with a far more sweeping, unsupported claim about cosmology's basic foundations. What makes this story genuinely worth paying attention to, without needing any exaggeration to justify that attention, is simply this. A telescope, specifically engineered to peer into the very earliest chapters of cosmic history, has repeatedly found galaxies that look considerably more developed, more massive, and more chemically mature than the physics developed before its launch. Predicted they should be, at points in time when the universe itself was only a few 100 million years old. That's not a minor curiosity easily explained away. It's a real, statistically significant, independently reinforced pattern, showing up across individual record-breaking galaxies, broader population-wide statistical surveys, and even entirely separate lines of evidence involving dark matter density within distant galaxy clusters. Astronomers are actively working through several genuinely plausible explanations, refining models of star formation efficiency, stellar populations, and early black hole growth, precisely the kind of careful, iterative scientific process that eventually resolves exactly this kind of observational tension, one detailed study and one peer-reviewed paper at a time. MOEM Z14 sits there right now, more than 13 billion light-years away. Its light having traveled for almost the entire history of the universe just to finally reach Webb's mirror, revealing a galaxy that, in the researcher's own words, feels almost miraculous, simply for existing as early, as bright, and as chemically developed as it apparently already was. Whatever specific combination of star formation efficiency, unusual stellar populations, and early black hole growth eventually explains exactly how a galaxy like this one managed to assemble so quickly. That explanation is still actively being worked out, one careful observation and one peer-reviewed study at a time, by astronomers who take this particular puzzle seriously enough to call it, quite literally, a cosmic miracle, right there in the title of their own published research. If you want to follow how this genuine tension between theory and observation continues to develop as Webb keeps pushing the boundary of the observable universe even further back, that research is still very much ongoing right now. Subscribe if you'd like to keep following where it goes next.